We were talking about energy in the earlier parts of chapter 3. So we need to talk about temperature. We also talked about states of matter and how the particles, atoms or molecules in a solid are actually moving. So atoms and molecules are always moving, even in solids. And that constant random motion is called thermal energy. So energy, thermal energy and temperature are related, and yet they're different. Temperature is a measure of the thermal energy. If the particles are moving faster, the temperature of that substance is higher. You know, if you touch it, it will feel warmer. So the hotter an object is, the more random motion there are among the particles. So I don't know if you guys really want to do this or not, but it would be cool. So you guys are all solid state students right now. You're sitting in your desks and you're just doing random little tiny motions. We could pretend to be a warm solid and have everybody wiggle. But I think you're all probably too embarrassed to do that, so we won't do that. But you can imagine what it would look like. Everybody just like chair dancing or something, right? You're still in the same relative positions, but everybody's moving a lot more. That's a solid when it's at a higher temperature. It has greater thermal energy. Another way to think of this is to think about barefoot people on a beach. So people in the Central Valley like to go to Pismo or the Central Coast in the summer because it's really, really hot here, and you go to Pismo and it's overcast and windy and it's like 60 degrees on the beach, and you sit there in your bathing suit wrapped up in your towel freezing to death. And we're like, oh, this is so nice, right? And the sand is cool, and you can walk and stroll barefoot and it's fine. Did you know that Reedley has a beach? There's even a sign. It's Reedley Beach. Yeah, she's laughing. It's a serious beach. But it's on the Kings River, which right now is just like this little stream. Earlier, before they released some water, it actually dried up in Reedley. It's really sad. But there's this big sandy beach in Reedley. Okay, so August, we just passed August. Are you going to stroll around barefoot at Reedley Beach? No, it's 105 and the sun has been beating on that sand all day. It's hot. How are you going to get from your car to the water if you're barefoot? You're going to run, right? You're going to hot-foot it, right? So people barefoot walking on sand, if the sand is hot, they're going to move very quickly because it hurts. And if it's cool, they can just stroll slowly. So particle motion, if the substance is cold, the particles are moving slowly. If the substance is hot, the particles are moving rapidly. In a solid, they're still stable relative to each other, but they're vibrating a lot. Okay, enough about that. So that's temperature. Heat is the transfer or exchange of thermal energy. So temperature is a measure of the thermal energy. Heat is the transfer of thermal energy. Heat flows from a higher temperature to a lower temperature, and it has units of energy. So if you put a piece of cold ice into a cup of warm water, we can all predict what's going to happen. The heat from the warm water is going to transfer into the cold ice cube. As the water loses thermal energy through this heat transfer, it cools down, and the ice cube gains thermal energy, and it warms up, and they come to the same temperature. That's heat. Heat is thermal energy moving. Temperature is a measure of the thermal energy. How do we measure temperature? Well, there are 3 different scales that are commonly used: Fahrenheit, Celsius, and Kelvin. Most of you are probably familiar with the Fahrenheit scale. That's what they record or report the weather. You know, it's supposed to be 89 today or something, 89 degrees Fahrenheit. On the Fahrenheit scale, water boils at 212. Water freezes at 32 degrees. Based on those numbers, do you think Fahrenheit is a metric scale or an English scale? English scale. The metric units use powers of 10, and the English seems to delight in random numbers. So 212 and 32. Doesn't make much sense. Room temperature is about 72, just for reference. The Celsius scale is a metric scale, and this is based on the freezing point of water. They said, well, let's make 0 the freezing point of water, and let's make 100 the boiling point of water. This is very practical because those are two temperatures that are very easy to replicate. If you have ice and water mixed together, you don't need any fancy equipment, you've got 0 degrees Celsius. If you boil water on the stove, you don't need anything fancy, you've got 100 degrees Celsius. And so you could make your own thermometer and calibrate it and be pretty good. And it's divided into 100 degrees in between. So this is the one that we're going to use most in chemistry. Another scale is the Kelvin scale. And this one is based on a concept of absolute zero. So here, 0 Kelvin, which looks a lot like okay, but 0 Kelvin is assigned to absolute zero. Absolute zero is the temperature, the lowest possible theoretical temperature, which no one has achieved yet, but they're trying very hard. At that temperature, motion of particles would cease. The particles would not be moving at all. It's a theoretical temperature. And the reason we use the Kelvin scale is because it avoids negative temperatures. And some of the equations that we're going to use, negatives become a big problem. So the Kelvin scale is based on 0 being absolute zero. The size of a Kelvin is the same size as a Celsius degree. So water freezes at 273.15 Kelvin, boils at 373.15 Kelvin, but in between, the number of divisions is the same as the Celsius scale. So what we need to learn in this chapter is just how to convert temperature from one scale to another. And this is done using equations. Because of the offset of the zeros, we can't use unit analysis for this. So these are the equations. Kelvin is equal to the Celsius temperature plus 273.15, and Celsius temperature is equal to Fahrenheit temperature minus 32, that quantity divided by 1.8. I will give you these formulas on an exam. I'll give you some useful information right at the top of the exam, and these will be on there. So, converting temperatures. Convert 358 Kelvin to Celsius. Well, we're going to need this guy right here. Temperature conversions always are going to require that we use a formula. So Kelvin equals the Celsius temperature plus 273.15. So here's the Kelvin temperature. We want Celsius. This equation is set up to start with Celsius and give us Kelvin. We need to rearrange the equation. Yeah. It's algebra. We can do this though. We want to get the degree C by itself. And so the basic idea here with algebra and rearranging equations is you want to do the opposite to get rid of something. So here this is adding 273. That means I want to subtract 273 from this side. So if I subtract 273.15 from this side of the equation, what am I left with? 0. This is 0, and I still have my degrees Celsius. But I need to maintain the equality. I need to do the same thing to both sides. It's like dealing with two children, you know, and if you give one a big cookie, you have to give the other one a big cookie too, or you're going to hear about it. It has to be fair. The problem is life isn't fair. So we need to do, but in math equations we can be fair, so I guess that's a positive. So then over here what we have is Kelvin temperature minus 273.15. So we have to rearrange the equation. And then a lot of times I'll just flip it around. I'll flip it around. I'll put the C on this side and this part on that side, just because it's easier to look at. So degrees Celsius equals Kelvin minus 273.15. I will be doing examples and talking about how I rearrange equations. If you are an algebra challenged person and need more help, please ask me and I can help you with this one-on-one. Okay? Please, because it's going to be hard for you the whole semester, but I'm pretty sure I can teach you how to do some of this simple algebra. Okay, so now we can do this. We've got the Kelvin temperature, 358, and we're going to subtract 273.15. So use your calculator. 358 minus 273.15. Syntax error. Obviously, I punched in something wrong. 358 minus 273.15. That's better. Calculator says 84.85 degrees Celsius, because that's what I'm calculating here. Degrees Celsius. Okay. What are we supposed to look at in our answer? Sig figs. Significant figures with temperatures can be a little wonky sometimes. So I'm going to tell you a shortcut that is actually better than using sig figs for temperature conversions. Look at where the uncertain digit is in the temperature you're starting with. The 8 is uncertain, right? It's always the last significant figure. So this temperature has uncertainty in the ones place. I want my converted temperature to end in the same place. The reason this works, for those of you who care, is that Kelvin, Celsius, and Fahrenheit degrees are all similar in size. They vary by less than a factor of 2. And so by converting temperature, we're not going to gain or lose significant figures in terms of where the uncertainty is. So this had uncertainty in the last place, in the ones place, and so I want to round this to the ones place. I'm not counting sig figs, I'm not looking at anything, I'm just rounding to the same decimal place as my number started out. So 85 is the correct answer. I'm also not going to specifically test you on sig figs with your temperatures. So
if you would have put 84.9, would that still be correct?
yeah, if it was like a lab or a worksheet and you were converting and you wrote 84.9, I would not count it incorrect. If you wrote 84.85, I wouldn't count it incorrect. I might, depending on how I'm feeling that day, I might write the correction in my nice fat red pen, but yeah, I wouldn't count it wrong. You have a question over here? Oh, okay, same question. Nice. Twofer. Any other questions? Let's do another one. Convert 139 degrees Celsius to Fahrenheit. We need the equation. The equation is degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. That was on the slide earlier. So here we're given Celsius and we're asked to find Fahrenheit. And again, the equation is not set up correctly. So we have to rearrange the equation. So the first thing I want to do is I want to get rid of this denominator. Here I've got Fahrenheit minus 32. It's divided by 1.8. To get rid of that, I'm going to multiply by 1.8. I'll do this in a different color. So I want to multiply by 1.8. Because what is 1.8 divided by 1.8? It's 1. So these guys cancel out. If I do it to one side, I have to do it to the other side. All right? So just for the sake of illustration, I'm going to write this out again so it doesn't look as messy when I do the next step. So that's what I've got now. I'm closer, but I don't have Fahrenheit alone yet. Here I have minus 32. How do I get rid of that? I add 32. Because 32 minus 32 is 0, and so there I've got degrees Fahrenheit. I have to do the same thing to the other side. So I've got 1.8 times the Celsius temperature plus 32. And that is equal to the Fahrenheit temperature. So degrees Fahrenheit equals 1.8 times the Celsius temperature. That's not 1.8 degrees Celsius. It's 1.8 times the temperature in Celsius plus 32. Okay, so now let's put the numbers in. Degrees Fahrenheit equals 1.8 times 139 plus 32. .8 times 139 plus 32. I keep pushing the wrong button. Delete plus 32. Okay, I'm getting 282.2. Did anybody else get that? Okay. And that would be degrees Fahrenheit. So, according to what I just told you about rounding temperatures, what should we round that to? 282. So we'll call that 282 because our original temperature was given to the nearest 1 degree. 139 to the nearest 1 degree, and so we should report this to the nearest 1. Any questions? Converting temperatures always requires that you use an equation. Oh, here's another one. Convert minus 321 degrees Fahrenheit to Kelvin. Was there an equation that related Fahrenheit to Kelvin? No. Does that mean that this is impossible? No. We'll have to go Fahrenheit to Celsius, and then use a different equation and go Celsius to Kelvin. So the Fahrenheit to Celsius equation was given degrees Fahrenheit minus 32 divided by 1.8. So that, thankfully, is set up correctly. We don't have to rearrange it. So let's put our number in, minus 321 minus 32. The quantity divided by 1.8. Now you have to be careful when you talk to your calculator. Minus signs, as you probably know, can be tricky. They can mess you up. So one way to enter this on your calculator is negative 321 minus 32. And I press equals, and that gives me minus 353. And that's divided by 1.8. I don't normally advise writing down intermediate values, but this is for a reason. And then if I divide that by 1.8, I come up with negative 196.11 repeating. And that's my Celsius temperature. Now, do it again on your calculator without writing anything down. The tricky thing is, if you just put in negative 321 minus 32, my thing's messing up again, and then divide by 1.8, you're going to get a different number. Because your calculator understands order of operation. Please excuse my dear Aunt Sally. Doing this is not one that you should be doing this on. Oh. All right, we're back. If you take negative 321, subtract 32, divide by 1.8, you're going to get a very different number. What you have to do is you have to tell your calculator, no, really, I want you to do the subtracting first and then do the division. There's two ways to do that. One is to take this number minus that number, press the equal sign before you press the divide sign. The other thing is to actually use the parentheses. This is a problem that will crop up over and over again during the semester. Percent difference and percent error is another example of where this happens, and also doing averages. Okay, so make sure that you know how to tell your calculator this to get this answer. Okay, and if you don't, come see me after class. Now we have Celsius. We can take this to Kelvin using the other equation. Kelvin is the Celsius temperature plus 273.15. I don't want to round this number yet because we're not done. We round at the very end. So this equals negative 196.11 degrees. Well, no, we don't want to do that. Minus 196.11 plus 273.15. Okay, and this gives me on my calculator 77.038 repeating, and the unit there is Kelvin. This is Kelvin, it's not degrees Kelvin. Now I can round this. How should I round that? 77, right? This is to the nearest one. And so I want to round this in the ones place. So this, we're going to say, is equal to 77 Kelvin. Any questions?